This is Paweł Kuśmierski. He's senior engineer and lead of Akamai systems operations in Krakow. He interned in Google as well in Mountain View, so definitely has some interesting stories to share. And he will talk about how much log can you hog. So applause for Paweł.
Thanks. So first of all, a bit of more of an introduction. I work as an operations person, which means I don't touch the code all that much. So if the level of detail is lacking, this is like sort of the ops perspective on some things. I used to do software engineering as well, so I learn about different things. But if you have any questions, I'll hope to answer them afterwards. So first, I'll tell a bit about Akamai. If you've pretty much the way we work is that we are, for the most part, we are content delivery network, which means when you're like downloading Microsoft Windows updates, they go through our network, or shopping on iTunes, or doing like different stuff on the web. We deal with a lot of making the internet faster and working. So this is where we are. A few numbers and some history about Akamai. Akamai was founded at MIT in 1998 by maths professor Tom Leeton and his doctoral student Danny Lewin. Actually, the story dates back to when Tim Berners-Lee moved from Switzerland to MIT to work on web, and they had a talk with Tom Leeton on the fact that the internet will probably stop scaling at some point, given the nature of client-server infrastructure, which basically has one server and many clients. So in the basic form, it will probably stop serving at a certain threshold when there will be more clients and servers. So Tom and Danny came up with algorithms which were basically supposed to offload the so-called hotspots on the internet. And they, as a sort of proof of concept, they entered a competition at MIT for setting up companies. They deployed their servers. They won the competition, got some investors, deployed servers around the world, and started serving traffic. The idea took off, and this was like the beginning of content delivery networks. So right now we have 150,000 servers in 2,000 different geographical locations in 92 countries. The reason I speak about it right now is that because we don't necessarily sell or accept data for our big data usage, but the way we do big data is from the logs which come from this platform for the most part. We've got a lot of logs because we pass through our network. Estimate is between 15 and 30% of the World Wide Web traffic, which is HTTP, HTTPS, some streaming protocols as well. And we're one network hub from like 90% of the internet users, or from their border router specifically. So basically, Akamai doesn't have the most servers in the world, but we claim to be the most distributed network, which is basically the furthest out there, so the closest to the users. And some numbers that we basically serve is, that we have the daily traffic exceeding 10 terabits today. I've seen something like 26 at one time, I think. We get 20 million plus hits per second. We have the amount of egress we serve is in the range of petabytes, and we do a lot of concurrent streams as well, because outside of just HTTP sort of website delivery, we also deliver streaming stuff. These are some of the brands that we serve, just to show that we're serious. We've got also military, and because we do we recently bought Prolexic, which used to do DDoS protection, for real, because we did DDoS protection just because we were everywhere, and if people were attacking, they would just be unable to attack the whole network because it was just in many places at the same time. And we also have DNS servers, so we can so we serve whitehouse.gov and other domains, because we just have a lot of machines and we can swallow the traffic. So The sort of basic idea behind Akamai is that you've got servers everywhere, and if you're like curious about hashing algorithms for like load balancing, there is a publication by Tom Leeton and Danny Lewin and a few other guys, which is called Consistent Hashing in Random Trees, which basically initiated the concept of consistent hashing that Google and some other companies are using right now. It's basically when you have a bunch of servers and they can go down at any given time, and you have an algorithm which maps objects for them to hold in cache. If they start dying at any given time, you change the domain of the function that maps objects, and you have to rearrange. If you have, a bunch of objects, it's not so bad. If you have millions of objects, a network in which servers go down all the time, you would have to move things, and you would lose any cache locality and any sort of use of cache. So consistent hashing is like a smarter way of locating objects and assigning them to the cache. And then again, if you have like 150,000 servers, if they would start connecting to the origin server of let's say, our customer, they could easily bring that server down because there would be just too many of them to serve. So the other concept called random trees is basically that you can arrange servers in tiered distribution. So you would have like the first level of servers, like customers would connect to these, and then you would have these connect to these, and then you would have, let's say, for every 50 servers, you would have one which would connect to the customer origin. And there was one very cool graph that I wasn't able to show just to get the idea. There was a recent software event where the origin traffic graph and the edge traffic graph was sort of similar, only the one was in gigabytes and the other one was in terabytes. So we would be serving like terabytes of traffic with only gigabytes of traffic from the origin server. Okay, enough of sort of high-level stuff. This is supposed to show like the development of big data inside Akamai and in the industry. So we actually, when we started deploying servers, we faced the problem of having to sort of build customers for our services. So we had to come up with a way to process our data, which was already pretty significant. And there wasn't like, there weren't open source project like Hadoop right now. So we just had to come up with a way of parsing the log lines. So in 1998, we came up with something we called parse and smoosh, which is basically MapReduce, but we didn't really, patent it or anything because we weren't in the business of, patenting stuff all that much, though we patented or tried to patent content delivery networks, but that's a different story. So we had a bunch of developments. So first, we had one machine could handle the sort of log splitting. Then we did the decentralized jobs scheduling and did a bunch of advancements on the front. And you see basically how the industry went right here. Right now, we are, these are some new stuff I sadly cannot talk about, but the white area stuff is that we basically have 90 data centers in different places because we sort of have servers all over, and we have to get our processing sort of also distributed. So we've got like around 90 centers against which we load balance and distribute jobs. So we have daily log data, which is the amount of incoming log data is 3 petabytes. Based on the fact that we just serve a lot of data, we have to log each and every hit to be able to provide analytics to customers and also build them and get money from it. Oops, sorry. Oh. Sorry, something went wrong with the slides. So it basically tells we have around 90 centers. We've got around 5,000 MapReduce nodes, and we process 10 trillion records a day and like 1 billion jobs. So like the 10,000 feet view is that we basically have the servers, the so-called edge servers, which serve traffic to the customers. this I'll talk about. This is like one sort of in-house built real-time big data system that is pretty unique to Akamai. We then have something which is called distributed data collection, which sort of sends stuff to our internal apps which do reporting. We can also deliver logs to the customers, and the devs can get it as well. So what do we sort of process in big data? We process logs. Obviously, we also have a bunch, a sort of a configuration files which are called metadata, like data about data, which is not very clear. Sure, sorry. So we also process system stats, different types of events and data about how the network behaves. And an interesting story is that we used to do it with email. So we would have every server out there, pack his logs and send it over email to our data infrastructure, which would just be a mail server, which would collect the, all the incoming email, and there would be, it scaled surprisingly well because up to 1 petabyte per day, it would just work just fine. And then we sort of thought, okay, maybe we could do something more professional about it. And so it's a bunch of guys came up with like a protocol. They showed it to our architecture board, and the guys at the arch board said, hey, this looks a lot like Speedy. Can't you just use Speedy? They said, okay. So we basically have a custom, well, we use Speedy for the most part with some custom stuff for signing the logs and make sure the stuff is distributed properly. With email there was also a lot of overhead for the headers, the encoding. So it's sort of funny, but when I started at Akamai, we would still just send logs via email, which was like 3 years ago. So we have some servers send log events over HTTP posts because sometimes we need like real-time data about attacks and stuff like this. We have SCP access for some reasons and some custom protocols as well. So the way this is like an example log line. This is a so-called compressed log line because it begins with an S, but we basically have multiple dimensions. We try to make sense with big data. So we have something called pipelines, and a pipeline is basically, you say, I'm interested in timestamp. I think this is this content publisher code, size, and the response code. So we have a bunch of machines which sort of deal with that, and we basically have a bunch of sort of formats we're interested in, which allows us to aggregate stuff by sort of different dimensions. And the way it used to work with email was that we used to have the queue layer, which was the queue like in queuing. Then we would have the P layer, which was the processing layer, which would just get stuff over like modern time protocols from the queue layer, then process it, and smoosh layer, which would do the map reduce. We would parse out data based on customer or different criteria. And the way we partition is basically we can also average. We're interested in like buckets which are time-based, content publisher-based, which is basically a way of representing customers. Also per network, so we can sort of plan capacity and buy servers where they're mostly needed. And we also have a way of like different hashing functions that allow us to distribute work better. One thing we use with load balancing is we have one of our VPs, when he was a research guy, came up with an idea of job stealing. So we basically sort of do the hashing and load balancing one way. Then if some servers are idle, they would just go ahead and go to the busy guy and just steal some jobs from him, and it works pretty well. we have a bunch of statistical methods for doing like probabilistic indexing and basically a bunch of different stuff I don't really understand, so I'm just not going to go too deep into that. We do combine values for doing sort of similar, basically statistics, which allows us to just do faster reporting and faster analysis. And the shuffle part is that we basically is the p-splitter part when we sort of try to get similar data in similar place to do the map reduce in a better way. And we basically have a bunch of uses. One is the query system, our real-time sort of big data system. DDC, which is the log collection. Media analytics, which is using DDC for analytics. We have security service that I'll talk about in a minute, and a log archive, which is, I think, pretty interesting use of sort of custom application of big data. This is like high-level view of the query system. So we basically have clients, and these are, I forgot the data comes from this side on this one. So we basically have all the servers sending data to the aggregators. The aggregators send stuff to the top-level aggregator, which these two roles are now combined on one machine. So you would have machines which can answer your queries in SQL based on the data they gathered, and there would be different clients, like people in the NOC or in different departments can just query the system directly in SQL. We have an alert management system, which we basically use for the NOC to fire alerts whenever like machines disappear off the internet, partitions get too full and stuff like this. And we have trend analytics and basically long-time data storage, because the nature of the system is that it's real-time and stores no history. So we have to sort of keep track of the stuff we've seen so far. This is a more detailed view of the data collection stuff. So the logs from the deployed network come in, they're queued, parsed, basically split into fields at the P layer. Then there are pipelines, which are the sort of specific to what we were looking for and sent for billing. We also do the shuffle and split stuff, do reporting on that, and sort of put it into Luna, which is our customer portal. Oh yeah, so here is the funny email part. Media analytics, it's not so sexy. The security products are pretty cool, because this is sort of recent that we started going into the security business. So we basically have a pretty short pipeline to be able to react in real time, because for like the DDC time, the time for the data collection is like on the range of hours. So we don't want to alert customers, say 5 hours after the attack happened, because it's not too much use. So we have a short pipeline for processing the security data. And here is where we have like, industry grade big data infrastructure. In the sort of DDC stuff, we have whatever we've built for the last, how many years it was. And one sort of interesting thing is that when you look at the ingest rate of our data collection system, is that it's exponential so far. So the guys did a kick-ass job of just scaling the system from 0 to the amount of logs we have right now. So we basically have a bunch of systems we do reports on and detect things like payment fraud and stuff like this. We're also replacing the database. We found some scaling issues and are building our own sort of custom stuff. The log archive has a nicer diagram in a minute, but basically what it is we have to store 90 days of data, and given the amount of daily logs, it's sort of challenging to do it. So we basically have a queue archive into which the logs come in, and right now it's the projected estimate for like in 3 years, which is the design objective for the current sort of phase of the development, is 1.2 exabytes. So it's just a lot of data which needs to be indexed, needs to be stored and processed. So if we would make a mistake in billing, or the client would think we made a mistake in the billing, we have to prove it with log data. So we have to just store the whole thing. And the way it's indexed is that we have to index it over IP addresses. So we have something called the client IP sketch database, which is basically attached to every record. And it basically allows us to, whenever we were looking for a particular IP address, we would just go to every single record. And based on the fact that we have a cache, it usually works in seconds for like the most common queries. But for the other stuff, it's sometimes, I know one instance where it took 14 days because the data center in which the data was just offline for maintenance. So the customer just had to wait 14 days for an unfortunate case where, the nature of the distributed network is such that you cannot control everything. So nice clouds towards the end. How well we are doing with time?
We're doing okay. Pizza is not here yet, so we can.
Okay, fine. Cool. So we've got a lot of data, obviously. And what we can do with the sort of the security stuff is we basically initiate connections from the edge servers. This 200K is, there are some fluctuations which sort of make it bigger than the amount of the servers we have. But basically we get real-time log data to our security infrastructure. So we basically have something called cloud security intelligence because it has to contain a cloud. We do analysis on it. We actually have a staff of people who are looking real time at the reports and try to find attack signatures that we can then apply to an automated big data system for looking for attacks in real time. So this is a basis for a web application firewall. So we basically have this working for our firewall use. So we have, apart from just being able to block traffic based on attacks, we also do something which is tracking client reputation, which is basically a reputation we assign to an IP address. And based on the data we have, we can see client behavior over time. And we use it to be able to predict behavior of specific IP addresses. And this sort of helps to track botnets because, like, when we were thinking about introducing this product, we saw that people would attack our customers sort of one by one after one. Like, the attacks were pretty highly correlated. So if we would find an attack on first customer, we can block the attack on another customer before it happened because we knew the client IP is malicious, and we are basically able to alert off of that. And this is like comparison to some other people who offer web application firewall. This is just to show the amount of false negatives and false positives is lower because we can see basically bigger portion of the internet. So the client reputation sort of works this way that we can, it's shared among customers and distributed. This is, and basically clients can define what they want to do with, let's say a hit comes in from such and such reputation. The reputation is scored on a 10-point scale. So if it's fishy enough for them, they can make the request take longer, present a specific page like 501, sorry, we're out of service, or just whatever they want. This is an example of just how it looks, just to get a feel. This is the sort of SQL injection or whatever the attack signature is, and whether it's it dropped, it increased, and you can do it for like specific IP address. So we just have to track a lot of IP addresses. So big data helps. Oops, sorry. The thing that I can talk about in more detail is query. This is our distributed real-time system, which right now it has 600 servers, and it has an SQL style interface that you can basically query through. This is like an example query. If you would like to sum up the amount of hits per continent, you can basically come up with this, semi-human readable SQL, and it will return a result. And this is the data has several guarantees that it won't be old, because we basically use it for like critical applications like alerting and making sure we know what's going on in the network. Before I go deeper into this, there have been several publications, like white papers by Akamai on the query system. So it's published. The source code is not published, sadly enough. It's sort of work in progress because we still discover sort of stuff just exceeds the amount of memory it has, and sort of we have to just scale it all the time. But it's out there on our webpage if anybody's interested in like more technical details of how this works. The general idea is that when you have a server, this is the query process, and these are different processes that are running on the server. This can be our web server, this can be the DNS server, and whatever else, log rotation client. So all of the processes report to the query process, and they would report. For example, our sort of general machine monitoring process would report the file system usage. This is like on one machine level. So each machine basically collects its own data. There is a query process which is responsible for that. Many different processes publish their own tables, and there is a snapshot taken every 2 minutes. On the level of a cluster, we would have a cluster proxy which collects all the rows from all the machines. So these are 2 servers. This is the row for the cluster proxy server. The cluster proxy server sums it up. So it has rows for every server in the cluster. There are usually several cluster proxies per region, per cluster, just in case one of them goes down, so that we have redundancy. And then we have a different sort of next layer of abstraction, which is top-level aggregators. And the top levels would collect data for the whole network, do snapshots every 2 minutes because there is a guarantee we won't serve data older than 2 minutes. And we also have static tables for data that doesn't change much, like the amount of machines that we have, their IP addresses, their functions, so we can sort of compare the dynamic state that's out there on the network with the static state that we have in our configuration files to make sure we have all the machines running. So, for example, our alert for whenever a machine goes offline, got crashed, stolen, burned up, whatever, is that it stops reporting to our query system, And there is basically a difference between a static CSV file that we have with all the machines we have and the dynamic state of the machine not being able to report itself into the system. So this is the sort of the TLA that I just talked about, the top level aggregator. And these are the SQL parser machines. So it used to be you would connect to the SQL. At one point it worked over Telnet. Right now it's like, custom protocol. And you would just type in select. And because these machines would have memory intensive stuff, because they would just fetch. Sorry, this is very old. But they would just fetch data and keep it in memory. And these machines would do the computationally intensive part, which is basically doing joins, indexes, and stuff. We combined the both roles, so right now this is one machine. So these aggregators, which is the TLA SQL thing, we have them for different networks. We have network which serves HTTP stuff, like unencrypted websites. We have HTTPS, streaming, internet load balancing, storage, different functions. So we have aggregators for different functions, for different networks. We also have it for different purposes. So we would have one purpose would be, for example, the NOC and like the operations part of the company, which has its separate set of aggregators, and also monitoring our customer portal and different things like this. We also, what we do is these machines sometimes crash because they're used heavily and we want to run them as close to the operating limits as possible. So we have our system which is called First Point, which basically connects to those machines, sees if they're healthy, and basically does load balancing over DNS. So the way you would do a query on one of those machines, you would try to resolve a hostname, and one of our load balancing systems, which we also sell to the customers, but we use internally as well, they would basically serve out the live server which you can currently use. Like I said, they're combined and they share DNS hostnames, which is the way we do load balancing. So right now we have, in the range of 600 these. They basically have a lot of memory because they need it and serve data, which is pretty recent. We're scaling it pretty aggressively. Okay, so that's pretty much it for the talk. I put a note here, which is basically that I went to a tech conference, like an internal Akamai tech conference in Boston, just like 3 weeks ago, and there was a competition between offices. So we have an office in Boston, in Cambridge actually, in California, in Bangalore, India, in Krakow. We've got a bunch of offices. Like I think 10 different offices took part, and it was like a software engineering contest internal to Akamai, and actually Krakow won, which was like really cool. And then one of the guys who's director of the big data department saw it and I don't have a big data, in Krakow, and so he decided to open one up. So we'll have a big data people in Krakow right now because we kick ass, right? So thanks, and if you have any questions, feel free to shoot.
I have a question. So you said you're billing customers based on the logs that you gather. So if you lose a log record, then you're losing money, and every time you duplicate a log record, then you're actually cheating the customers.
Yep.
So how much data do you lose, and how much data do you duplicate?
So it's much easier to lose data than to duplicate it, because we basically TCP ensures we don't duplicate on the network level. And whenever we just deliver a file, we sort of delete it. So because it's just a lot of data on the servers, so we don't want to keep more than we have to. We'd rather lose data, sort of, because customers pay us like a platform fee, and in addition, they're billed by traffic. I don't actually know how much data we lose, but I know that whenever we have a machine in the DDC network, which goes down for maintenance, there is like big banner, you cannot rescue the machine, which is basically insert a rescue CD which erases all the data, because we would lose a lot of money. So we sort of try to make sure this doesn't happen this way. And if there is a maintenance to be done on such a machine, it cannot be touched for 45 or 90 days, which is like, come on. But yeah, just to sort of make sure we sort of get paid in the end.
So how often do you get such failures of machines?
Pretty much. So you mean specifically billing ones or generally?
No, generally.
Part of my onboarding process is I worked in the NOC, and in the NOC you basically watch alerts and run procedures. So I don't know how many people at the same time would have to do the disk errors procedure, which basically deals with the errors on disks, but it wasn't one person. And it was just like constantly they would come in and you would make sure this happened, this doesn't happen, check DMS, and it was just a lot of stuff. So I don't have the numbers.
Can you automate this in some way?
It's pretty much automated, but there are certain steps we have to run manually. We don't we contract out disk replacements, so this is like sort of thing we can safely offload, but we have like some operational steps we sort of have to do ourselves, like the OS install. It's pretty like, what's pretty cool is that we don't use like DHCP, TFTP for like starting up servers. We sort of, I guess, started doing it before it was like popular or cool, and we do it sort of differently. There is an IP address statically configured on a machine, and then we can just, as soon as it's SSHable, we just do everything remotely. Mm-hmm. But it's initiated by a human being. So there are like certain steps which we have to sort of manually kick off.
You said that you are replacing HBase with some custom solutions for the security parts. So can you tell us what specifically is the scaling problem?
There was some problem with, I think it was horizontal scaling. It just, the way we were using it sort of didn't work. I don't have details on it. There is a unit in Israel which is working on this specifically. I just know it's sort of stopped scaling, and we had our own sort of expertise in the area, and we came up with two systems which are going to replace it, but I don't know much more than that.
You also mentioned that you're replacing SQL parser in Hive. So is it to make a better compliance with SQL standards? Or?
This I entirely don't know.
Okay.
So I know we're doing it, but I don't know the real design decision, sorry.
Do you get any plans for moving to IP6?
Yeah, we are actually, so the way we sort of deal with global traffic management is that we do maps of the internet. So we also do maps of the V6 internet already. And we also serve websites over Internet v6 when customers don't really support it. So we can have our server connect to the origin server over IPv4 and then serve the website over IPv6 and stuff like this. An interesting thing is that the v6 internet is different from the v4 internet. Has some sort of different subnetting and characteristics.
So the whole network is ready for the v6, right?
The front end sort of is ready. To be like absolutely frank, we still have some stuff to do internally because there are some assumptions which were made, 1998, with maybe not having IPv6 in mind. So the migration internally is still going on. The most important part, which is the serving and internet mapping, are completely swept off. So we do these.
So you have this petabytes, exabytes of data, all of data, and after aggregation, how much data do you have, and how do you handle it, and where do you store it, how do you process it?
So we store the data in the log archive, and these are pretty much raw, pre-raw log files. Have to get back to. So this is a slide about log archive. So this is like the deepest level of the archiving we do. So this is 180 petabytes that we sort of keep in the archives. They are.
This is all data, I mean, unaggregated.
So this is data for the whole network for 90 days. This is kept on different machines. There are indexes. There is archive index which has 10 terabytes, and the client IP sketch. This one is like more centralized, kept on HDFS. The client IP sketch database. This is kept on the servers themselves, and there's another way because the sort of IP space per hit is sort of too large to sort of centrally store in any meaningful way. So the archive index basically has pointers to servers and to log file locations. The client IP sketch just lives on the servers and says this file contains entries for these IP addresses, and we sort of do look up this way. If we're looking for an IP address, if we're looking for more high-level stuff, we do it sort of in a more centralized way.
I guess we don't have much more time. As you guys in the back can smell, the pizza already arrived. So big applause for our speakers.